All right, welcome back to the one slide series, Control Systems Unlocked. We were looking at representations of dynamical systems, and today we're going to look at state space representations of dynamical systems, which we are going to use a lot throughout these lecture series in what follows. So let's start with an example. We have a third order system y dot 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 equals to minus 4y plus 2y dot dot plus 6. And well, in the last class, we can represent it using a transfer function, but here now we're going to represent it in the state space formalization. If you are not familiar with it, don't worry, I will guide you step by step. The ultimate aim is to write any differential equation that are linear in parameters into this compact form. And if I teach you how to control this compact form, then since you can put any linear equation into this form, then later you are going to learn how to control any system. So putting this system into this compact form is very important. And how we do this, if you have a third order system, you need, so the highest order is 3, so you need 3 states which are related to y dot, and y dot dot. If you have a fourth derivative, if you are dealing a fourth order system, then you need x4, which is y dot dot dot. But in this case, the system highest order is 3, so we need to go all the way to this highest order minus 1 derivatives, so second derivative, like this. And when you differentiate these variables, x1 dot becomes y dot, but y dot is x2. So x1 dot is x2 here, 1 multiplied by x2, 0, nothing else. If you differentiate x2 dot, you get y dot dot. So x2 dot is x3, since y dot dot is x3. So x2 dot is x3 here. And finally, if you differentiate x3 dot, which is y dot dot dot, and y dot dot is basically this equation, minus 4 multiplied by x1, x1 is y, nothing in here, 2 multiplied by x3, because you have 2y dot dot, which is y dot dot is x3, and then you have 6u, which is the here. And the output of the system is y, the first state variable x1, so you get this 1, 0, 0. This is your A matrix, this is your B matrix, and this is your C matrix. In this example, you don't have a D matrix, so that's why this is gray. D is 0 in this example. So we only look at this yellow part. This is our system. And I will cover one more example. I'm particularly trying to select those examples such that even if I cover 2 examples, the formalizations that you see here, you can apply to any other ordinary differential equation, the same steps. So this was the first example. Now you can recover the transfer function from a state space representation, and it is quite straightforward. So I will talk about uniqueness. So, well, we have this representation x dot equals to ax plus bu. I am going to the Laplace domain. So with 0 initial conditions, whenever you see x dot, you have si. So we have s multiplied by x equals to axs plus bus. Now I am sending this to the left-hand side and grouping. Basically, we have s. Since it's a scalar Laplace variable, I need to put an identity matrix here because this is an n by n matrix in general. In our case 3 by 3, but in general n by n. So si minus ax equals to bus in the Laplace domain. So you can set this to the right-hand side. You basically multiply left and right by the inverse of it. So you have x of s is si minus a inverse bu. Now you care about the output. Output is c multiplied by x. X is here, so y is c multiplied by this expression, or you can write this in the transfer function form, y over u equals to c si minus a inverse b, this guy. I just sent u to here, to denominator, outputs divided by the inputs. And if you put this C, A, B matrices and take the inverse patiently, you are going to get this transfer function. So you can always go from state space to transfer functions like this. Or if you have a transfer function, you can also write the state space formation. All you need to do is, use this and this, y multiplied by the denominator equals to u multiplied by 6. And once you get y multiplied by the denominator, you have y dot dot dot, which is this guy, minus 2 s to the power of 2 multiplied by y, which is this guy. So basically, if you do this multiplication, you are going to get y dot dot minus 2 y dot dot plus y equals to 6u. And if you send y to the other side, you are basically recover the this ordinary differential equation. Basically the same process, but backwards. So if you have any questions, you can leave the comment and I will try to answer. The main um, important points are two of them, two important points. The number one, eigenvalues of A that you see here, this matrix as eigenvalues equals to the poles of that transfer function. What are the poles? Basically, take the denominator, set it to 0. So poles of that transfer function or the denominator of this equals to the eigenvalues of A. And I put an exclamation mark here because this is a heads up. If the system is controllable and observable, then eigenvalues of A equals to the poles of this transfer function. And most of the time in practice, systems are controllable and observable. If not, we need to be patient and we need, later maybe I can cover this topic. It is not very important since most of the systems we deal with controllable and observable, but still it's good to know if this is not the case, eigenvalues of A can be more than the poles of the transfer function. But again, so under the controllable and observable assumption, eigenvalues of A equals to the poles of the transfer function. I think we should remember like this. All right. So now, about the second point is the uniqueness. Transfer functions are always unique. So, what I mean by that, so for example, state space representations are not unique. I can easily illustrate this by, we choose the order of the states like this. You can ask, why not choosing x1 equals to y dot dot, x2 equals to y, and x3 equals to y dot? You can also choose it like this. All you need is three state variables that covers one less than the highest derivative. So when x1 is y dot dot, these ABC matrices will slightly change, but still it represents the same order. It will represent the same order in differential equation. But whenever you get, for example, when you reorder the states and get this representation, a form of this representation with different ABC, when you calculate the transfer function like this, you are going to get the same transfer function. So from this standpoint, transfer function representations are unique. However, when you reorder the states, you can find different state space formalizations for the same problem. So state space representations are not unique. Does it create a problem? No, not at all. So let's move forward. Now, the second example is when we have input derivatives. When we have input derivatives on the ordinary differential equation, we follow a procedure that will help us to put those ordinary differential equations into the state space forms. First, we write the transfer function, actually, for this purpose. We take this ODE, transform it to the Laplace domain. We have s to the power of 2y. I am sending this to the left, 2y, equals to 3 multiplied by 4s to the power of 2u. And now I am trying to write it as output y equals to this transfer function multiplied by u, which is coming from this line. So I am going to make its numerator green multiplied by w, and w is 1 over s to the power of 2 multiplied by u. Essentially, this is the same transfer function, but I am breaking it into two parts. The first part is this w, half w, it is like the virtual output. It is not output, but we just assign to be, this virtual output related with the inputs. And then this virtual output multiplied by this green transfer function will create the actual output. And here we always do the same treatment. Keep the numerator here like this, whatever ordinary differential equation you have, and the denominator, just put it there. We separate it like this. And after the separation, first we look at this relation between the actual control input and the virtual output, which is W over U has this transfer function. Like I explained here, we are going to do the multiplication, W multiplied by S to the power of 2 plus 2, which creates W dot dot plus 2W equals to U multiplied by 1 is U. So from here, we recovered this ordinary differential equation that represents how input affects our virtual outputs that we chose. And here you can now define state variables first for the system, since second order system, so we need W and W dot. Once you do this, you can write this state space form, similar how we did here. You can pause the video, go through this process. Now, when you have input derivatives, getting an output will not be as straightforward as this for the case when you don't have input derivatives. So when to get the actual output, because the W's are nice, but the W is not our actual output, right? It's virtual output. Our actual output is this transfer function multiplied by W. Now I am going to the time domain, y equals to 4 multiplied by W dot dot plus 3 multiplied by W. And grouping things, basically W dot dot is this one. W dot dot is minus 2W plus U. I am inserting is here. And sometimes you see dependence of time. Sometimes I dropped for the clarity. I am dropping time here because this was Laplace, this was time. Obviously, I am continuing here in the time domain. So after you insert this equation here and organize here, right, minus 8W plus 3, it has minus 5W. W is x1, right? We assign it to be x1. There is no dependence on x2. And now we have 2 multiplied by this should be 4 multiplied by u, my bad. So I just wrote it incorrectly. So now we have this expression, and the first line is here, x that equals to ax plus bu, and the second line, c is minus 5 and 0, x. Now we have the du term when you have input derivatives, in this case 4. 4 multiplied by u here is the d matrix. In this case, it is 1 by 1. So this is how we go from ordinary differential equation to the state space formalizations. Again, 2 examples here. All you need to do is to define the state variables the way I describe it to you, and then write it in the state space form with or without du. If you don't have, in order to get du term, you need to have a derivative of u that is equal to the highest derivative on the output. So if you have u dot, you are not going to get du. So it is very specific. For some specific applications, we get this du term, but when we get it, we need to treat it accordingly. So anyway, we covered state space representations. If you have any questions, you can ask, or thanks, and see you in the next lecture. Take care.